Hello everyone, welcome to the bridge building competition hosted by SAICE, and this is the Western Cape branch edition. Now normally I'd get an opportunity to give this presentation to you in person at the central venue, which could have been Sanral buildings here or the Century City buildings. However, I'm doing it online. COVID has changed many things about the way we do the competition, and maybe the most exciting thing is that you can now build the bridge in your own time and at your own school or at home even. The purpose of this presentation is to give you some information about bridge building, things that you should consider when you design your bridge, and hopefully some tips on how to do it. Now, before we get started, I just want to acknowledge a few sponsors, in particular Alkaline, who donated all those fantastic glues that you received in your kits, as well as Bestwood Joinery, who went out of their way to make sure that we had our wooden struts ready for us to use in this competition. Also, we have received financial support from a number of companies, including Hatch, Zutari, PRDW, JG Africa, and MPM Art. I'd like to thank all of them for their generous contributions to the competition. So, what is a bridge? Is it simply any structure that allows you to overcome an obstacle? So in this case, a palm tree, which is over a river. Is it something that's beautiful? Something that's designed to last a period and people can be very proud of? Is it something that is unusual to get across obstacles which you normally wouldn't be able to overcome to enable you to get access to another place? Is it curved? Is it big? Is it beautiful? Is it something that moves, like this bridge, which tilts up to allow boats to go underneath it? Or this one maybe? Or is it temporary, like this example of a floating bridge? Well, in our case, a bridge is defined as something that bridges a gap to enable you to get from one side to another. You could use the analogy of the London subway, the London Underground, apologies. So I'm going to talk a little bit about structural theory. First of all, beam theory. So a beam is typically a structural element which is orientated horizontally. And a beam typically has its own weight, and if you were to walk across it, you would impose a mass on the beam and it would start to bend down. I think that's fairly intuitive and you would understand that. And that your force, your weight, would pull it down and it would bend up. Now, it's really useful to try and understand what is happening in the structure. So we're going to try and analyze it, and we're using two colors, red for compression and green for tension. Now, before I show you the next slide, I'd like you to imagine you've got a piece of foam, a rectangle piece of foam in your hands, and you bend it so that it pushes down. Now, what happens to the top of the piece of foam, and what happens to the bottom? You may notice the top starts rippling as if it's in compression, and the bottom is stretched as if it's in tension. And that's exactly what happens to our beam. The top elements are in compression, and the bottom elements are in tension. Now, this concept is very useful, and we'll use it a little bit later in our discussion. Now, what happens if you put too much load on that beam? So, for example, an elephant walks across the bridge, and the tension forces that the bridge can withstand are no longer sufficient for the weight that the elephants put on. Well, the lower tension members will effectively snap, and as soon as they do, the depth of your beam is decreased, and the whole bridge will start collapsing. What about columns? So columns are elements that are orientated vertically, and we define them as columns and struts. Columns are typically always in compression, so there's typically a force that's always acting on them to hold them down. Struts tend to be longer, more elegant elements, thinner elements, and they're more prone to another factor called buckling. So although they're always in compression because they're being pushed down, they tend to buckle out to one side. So, in summary, beams experience a combination of compression and tension, and we note that the stress is concentrated at the top and the bottom of horizontal members. Compression members, such as columns and struts, typically can fail by buckling. So now we're going to look at a girder type bridge. So we've got elements on the top oriented horizontally and elements on the bottom oriented horizontally. The top is in compression, the bottom is in tension. Now we put a series of vertical elements, columns or struts, holding them together. Now this is what we call a girder or a truss, and if we were to apply a force on the side at the top as shown, you can probably see what's going to happen. Like a bunch of dominoes, the whole thing is going to start tilting to one side. This is because rectangles tend to be reasonably unstable. Although these structures can work, they require an immense amount of reinforcing at the intersection points between the columns and the beams. Now, if you want to get away from that, you're probably already aware that triangulation is a very strong configuration. So if you to then introduce a whole bunch of triangular elements or diagonals, then you'd probably end up with a much stronger solution. And these could be configured in one of two ways as shown. Now, what do these configurations mean? Well, if you look at the configuration shown here, you can see that because the loading, in our case assumed to be in the middle, is pulling the structure down, it is putting those struts that are diagonal in tension. And because they're in tension, they're very stable. They don't want to buckle. They don't want to pull out position because they're being pulled straight. Now, if you'd orientated the struts in the other direction, where the bottom is being pulled out, you would agree that they're being put into compression, which now makes them unstable because they're now liable to buckle. So one way of addressing this is to say, well, if we did diagonals in both directions, then we'd effectively shorten the spans and enable the elements that are in compression to withstand much greater forces. And what you're doing here is you're pinning the struts to each other at the midpoint to ensure that you get as short spans as possible between loads. Here's an example of a steel girder bridge across the Orange River. Now, if you look at the bridge from above, it too needs to address horizontal buckling and to make sure it's stable. So we apply bracing across the top as well. This is as important as when you look at it from the side. Now here's an example of the Firth of Forth Railway Bridge in Scotland, where this was used probably to an extreme point of view. And here's the same bridge, but with a different angle. You can see the crossing across the bottom to give it stability. Now we're going to look at a different type of bridge, the arch. The arch has one really important characteristic about it, and you can probably guess that the entire structure is under compression. Now this is really useful because we don't have any tension members, and structures that are always under compression are quite strong if they don't buckle. In this case, they can't buckle because the elements are fairly squat, so they can't just push out. Now, the structure effectively is putting all of its weight directly onto the ground because it's all orientated down. Here's an example, the Alcantara Bridge in Spain. However, if your arch isn't restrained, it will push out on the sides. So it's going to push out on the sides and it needs to be restrained. This can be achieved by anchoring it. So for example, the Lowens River Bridge, as shown here in Somerset West, has buttresses and foundations which restrain the arch to prevent it from moving out. Here's another example of the Blowcross Bridge in the Garden Route, where the arch is anchored into the slopes of the Blowcross River on either side. Now, an alternative way of restraining it, instead of tying it to the ground where it is located, is to actually install a horizontal member which restrains the arch itself. This is called a bow strainer arch, and effectively provides the necessary restraint. Now, another approach to designing a bridge is to suspend your elements across the gap. So you could run a string across, or you could run a rope or a cable or something else. And this certainly has been an approach which has been around for quite a while. However, this has been taken further as materials have improved, and here's an example of how suspension bridges tend to work. They will have a suspended cable which runs across above the bridge area, and then the decking is suspended off the cable. The cable itself is supported off columns which run on either side, and the approaches typically have an arch, as is shown over here. An important part of suspension bridges is that the cables need to be well anchored, because there are incredibly high tension forces that are at play there, and you must ensure that you specified your cables correctly. So a good example here would be the Storms River bridges, the suspension bridges at the Storms River mouth, or the Milan Viaduct, which is in France. This is the Millennium Bridge in London. Interestingly enough here, the cables on which the bridge is suspended are oriented on the side rather than above necessarily. The Verrazano Narrows Bridge in New York. Now, what's interesting about this bridge is that you would notice that the cables are quite big. So how do you design and build a cable that size? Well, actually, you have many, many cables or strands that make up each of those cables, and they would have pulled these strands over individually and then locked them together as these enormous bundles of cables of 26,000 strands each. And here's the Golden Gate Bridge in San Francisco. So when your bridge is placed, it will be supported on either end and will be loaded in the middle. And those points where the loading is are the most important points that need to be reinforced. So where it's supported, you can experience a force called shearing. This is a vertical force where the one point is pushing up and the other point is pushing down, and it wants to rip itself away from itself. So ways to address this are firstly to make sure that your bridge is designed so that the support structure goes all the way to the edge of your support area. So you can see in this example, the bridge itself is not actually wide enough to give support all the way to the edge of the deck. So with this better, but even better still is you would provide additional support to the bridge on those edges. So we've now learned that tension members are very efficient. Bending is good, compression is better, tension is best. Now, what about the aesthetics of a bridge? So, bridges are pieces of municipal infrastructure, and as a result, they need to look beautiful. So we want you to also think about how beautiful your bridge could be, depending on how you design it, how you can make it look fun and interesting to you. So just changing angle can change the perspective of a bridge quite a lot, and we'd love you to play with that too. So what will bridges of the future look like? Well, it's highly likely they'll get longer and longer. For one, bridges are really a function of the materials that are available to the bridge designers. For example, there is talk of the Gibraltar Bridge, which is likely to be 14 kilometers long, and some of the designs for it have indicated support columns of up to 910 meters tall, with spans of over 5,000 meters. But here's some other ideas of bridges. These are post-tension bridges, where elements are precast, floated to site, lifted into position, and then cables pull those elements back onto the main bridge once they're in position. Or, what about this bridge in Shanghai? It's absolutely amazing what you could create once you understand the principles around bridge building and how you can make things work. So, thank you for listening, and I wish you all the best for your bridge building competition. It's a really fun competition, and you will learn lots from building a bridge. Please let me know if you have any questions, and we're looking forward to breaking your bridges in a month's time. Bye.